move on to the concept of what's so-called higher derivative. Or precisely speaking, higher order derivative. Now I'm talking about higher order derivative, so it's a plural actually. Okay. And then so before I get far, get really anywhere further into this, how about let's make a table like this. Okay. So let's say this table is also introduces the notation. So as far as the function level, right? When it's the original function, we have two commonly used notation, right? Either as f of x notation, you know what I'm saying, no? Or the famous equational format, y equals some expression of x. You guys follow it? That's just the notation, right? And so we have learned up to this point in our learning, derivative, when you find the derivative, right? So the derivative, if we're using with the functional notation, and we go with f prime dash for that, you guys agree? Okay, that's this notation for general derivative. And then use the dy dx, the Leibniz convention symbol. When your equation was originally written in equation format. So now with that, the story kind of like, let's put a pause on that right there. Let me go back to a very simple problem. Let's say x to the 6, right? You got a function, y equals x to the 6 right here. Now if I'm asking you to find the dy dx, right? And you guys know what to do immediately on this, right? It's just the x to the 6 to take the prime of that, right? And that's making it 6, right? X to the 5th power. Sounds good? But now I've been arguing at some point earlier that the general derivative, those general derivatives we've been finding so far, they are in the end another function, right? Aside from that original function. So the original function is one function. And then this guy right here is another separate function right there. See what I'm saying? Derivatives are functions itself, right? But it depends on the input x variable. So in that way, think about it. Once you have arrived at that derivative, can I ask you to take that as a function and ask you to do this? X to the 5th, 6x to the 5th, right? Take the prime again. See what I'm saying there? Right? You got the very starting function, you got x to the 6, and you arrive at this guy right here, and you say, hey, this is the derivative of that, right? But then on that derivative already found right here, we take one further derivative. So it's sort of like the derivative on the derivative, right? What's the answer for that? Yes, it's 30x to the 4th, right? It's another function, right? So can we take the prime on that at 30x to the 4th? Okay. Right? Sure, why not, right? If there is an application out there, sure is, there is application out there. So we'll take the prime of that 30x to the 4th. Because again, each step that we took the derivative, that derivative came out as a function itself. See what I'm saying then? And so, treating this as a function, you can surely take the derivative on that function 30x to the 4th, right? Which is making it 120 x cubed. You guys following? Okay. And so now, all of a sudden we realize, out of some starting function, this is what you can do right here. So, the starting function is the original function. Now, with this original function right here, this derivative, we took that the first time, right? So we call that, now with this term here, we call it as the first derivative in respect to like the very, very beginning function. See what I'm saying? Now we took the derivative first time. So this 6x to the 5th here is called the first derivative. You guys follow with me on that again? But so now that means what? Starting with this point right here, we took the derivative, we took another derivative, right, on top of our first derivative that we originally found. Okay? So this guy here, which came out 30x to the 4th, relative to the beginning one, the very beginning function right here, now we call it, guess what? Second derivative. See how I'm saying that right? So this one right here, right, is the second derivative. And so I'm saying second derivative on behalf of, if we compare that to the very, very original function. So we took the derivative twice on that, right? You guys get the idea? But so you got, and needless to say, the second derivative is the first derivative of the first derivative. Because it's only one step that we took derivative from our first originally found derivative. You guys following my explanation on that? So each time we produce that, we only take one derivative, but it's on top of the precedingly done one, right? So guess what? How do we call this guy? The third derivative. There you go. Third derivative. Yes. So simply take the derivative of the second derivative, right? Gives me the third derivative. Yes, that's how we call it. And so now in that way right here, yes, you can technically keep going, right? You can take the fourth derivative, take the fifth derivative, and those, see the first, the second, the third derivative, those I so-call them the order of our derivatives. Sounds good? Like when you say the first derivative or the second derivative, see precisely we call it, it's the order of our derivative. And so now we're learning out in our quarter, we first always learn out about the first derivative because that's where our skills came out. And then once you're fluent with that, then moving on to those higher order derivatives, it's going to be easy. See what I'm saying? Okay? And so in that way, now I'm going to put it further into my chart right here, and you can understand the symbol a little bit even more. So here's the idea. So it's just as far as the symbol. So now, yes, that's derivative we usually know, right? Comes right out from any function. We call it the first derivative. Okay? First derivative. And so the symbol is that. You see how I use the F prime right there? And then the UIDX, if it's the Leibniz symbol, right? So now, so in that way, you have just now learned, and it makes sense to have, as far as still, the derivative, right? But we now have the second derivative. Sounds good? Right? So guess what? Think about the symbol here. It makes sense that people use this. The F prime, but we prime again. So it's the F double prime, the F prime prime, right? The F double prime, that's the symbol for the second derivative. Okay? Relative to or on behalf of the very beginning original function. Okay? And then the Leibniz symbol is starting to get a little hard to understand, but think about it. You put, it's actually, so second derivative, you put the square on the d right here, so it's d squared y, okay, over dx squared. So why is it looking a little strange like that? Kind of like out of order, right? The top square right here is on the d, but the bottom square is always on the x. See what I'm saying now? Here's the reason why. It's sort of like this. You got some functions, right? I believe I've been explaining quite often about the symbol, the Leibniz symbol here. The idea is we have this operator, the d dx, we apply on top of that, indicating we want to differentiate the function y. You guys following? And that's why we got the d, for short we write it as a dy dx, right? But originally we have what's so-called a d dx. The operator right here indicating we want to take the action, we take the derivative on that function y, on that objective function to get the dy dx. And so now think about the second derivative. We do another level of derivative, and that means what? On top of whatever here, right? We differentiate again in respect to x. See what I'm saying now? Right? So you took the one derivative in the inside here first, right? And then whatever you've done with that, you take another d dx, you apply another operator d dx on top of that. That's why it works similar. It looks like a multiplication that, hey, when you put all together, see d and d, it makes a d squared. See what I'm saying now? Okay, and then there's dx together, mixed together, that's why it's a dx squared. That's the idea right there. Okay? But it's only, basically, we treat that as an operator, as a symbol. Right? But it doesn't really mean multiplication. Okay, so don't take that as multiplication. Okay? It's far from being a multiplication. Right? And that's the reason why we arrive at things like that. So that's the second derivative. So now what do you guys think? I can keep extending this table further down, right? For the third derivative, for the fourth derivative, and so on. So here's the thing. A couple more lines and you will get a very general idea of this. And right now I'm just introducing the symbols, the notations, the way how people run notations out there. So when it comes to the third derivative, right? The third level, and of course, relative to the beginning original function right here. And yes, it makes sense that we put the 3 primes, right? So F triple prime, that's how we call it. F triple prime, the 3 primes there. That's the symbol in functional, but the notation right there. Triple prime of f. And then, yes, here is easy enough. It's d cubed y, right? Over dx cubed. You guys following? Okay. But now, things starting to get a little weird here. But now I'm going to have to say when it goes to fourth derivative, right? Fourth or higher. So fourth or higher derivative. And here's how we're indicating it. We put the order in as a superscript in parentheses. So like fourth order derivative, like the fourth derivative, we go like that symbol right there. Instead of go prime, 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 prime. Because it's ridiculously too many primes, right? And think about it, ideally there have been people finding the 100th derivative. Are you having enough paper space to draw 100 primes in there? See what I mean? Okay, so that's why I was saying as a convention, worldwide convention right here, then starting with the fourth derivative or higher, we put the order in as a superscript in parentheses. Okay? And textbooks worldwide will use that. Okay? So we go with that. Sounds good? But then the Leibniz notation then still go the same. Y, d4, right? Y over dx, the fourth. Right? So on and so on. You guys with me now? Okay. So please don't write on your paper that hey the fifth derivative you 1, 2, 3, 4, 5 primes like that. It's way up the hook with that. I mean it's not wrong, but you're talking about you're making yourself stand out from a real big majority of people the way how people use it out there, right? And it's gonna cause serious misunderstanding. And then I should have mentioned this, but on your table here, how about you guys extend for me 1/3 column right here. Third column, one more column. I hope you guys still have space for that. Okay, so because these are just the notation. And so, like, these are the two unique ways of how we write our notation for the beginning functions, right? So the beginning function can be either written in the functional format or in equational format like that. And so we come to when it comes to calculus, we come to a hybrid notation for the derivative, right? Sort of like a mix between, so I mentioned this a little while ago too. So for short, sort of like hybrid for short, it takes two conventions together and put it in one short. Like say your equation is in a y, in the equation format, you go with y prime like that, right? So you adopt that prime symbol, right, together with the dy dx equation over there, you go y prime. But this thing, of course, is lacking a lot of indication about who's the main variable. You got to know your equation. See what I'm saying? And it's kind of default that whatever your equation is written in, and so sort of like it's default. It's good use for when your equation has only two variables. And then if you take one to be the function, right, and the other one remains without indicating, it's the main variable. And so just like that. Second derivative, the hybrid version, you go y prime prime, right? Y double prime for short. And then yes, third derivative, you can still go with triple primes. The hybrid version for your notation. And then when it comes to fourth derivative or higher, you still have to put the order in as a superscript in parentheses. So that's the hybrid version of those symbols. Am I making my point? And now even further. I mean, there's more fun, right? It's awesome with these stuff here. Think about I brought up that quick little demonstration problems, right? We're starting out with our function being x to the 6. You guys all agree? Right? And then so now that means what first derivative was, it was 6x to the 5th. You guys all following? We call it the y prime whatsoever, right? See? Should have written that as y prime equals 6x to the 5th. And then we got the second derivative, right? We call that as y prime prime, right? Or y double prime equals 30x to the 4th. We're good with that there, right? And then the third derivative and so on and so on. Right? I don't need to keep repeating that loop. Right? Third derivative, 20x to the third power. But now we've been looking at those higher derivatives, So now you can think outside of the box a little bit. if you keep backtracking it, right? If you keep backtracking it, think about the function itself here. If this guy is the first derivative, what do you think as a derivative order, what do you think that the original function can be regarded as?
Just zero derivative.
Yeah, yeah. See, it's just sort of like a convention. See what I'm saying, no? Okay. So yes, we call original function. We call these guys first, second, third as the order, right? So as far as the order, we didn't take any derivative here, right? That's why we call it as a zero derivative. Yes, I agree with that. Right. So original function right here is also regarded as, and also open parentheses here, it's called the zeroth derivative. No, I shouldn't use number for that. That's that concept of the zeroth derivative. All right. Now I have something good enough for you guys to explore here. So with this same demonstration problem I brought up, it wasn't any formal example yet. So we found the third derivative, right? By the way, if you need to, you use a calculator, okay? But so if I was asking for the fourth derivative, right? Fourth derivative, then it comes out what? Fourth derivative equals, right? That multiplies down to 360 x squared. You see what I'm saying, huh? And so, but the idea is that originally our function was a power function, right? Our function originally was a power function. So in every step we took the derivative, that power reduced by 1 and reduced by 1, remember? Okay? It's all the power rules that we've been learning with that. So we got down to 360 x squared. And then there's when it comes to the fifth derivative, right? What do you say? Yes? Y, right? Superscript. Fifth power over here, fifth order right there, making it 720x, right? And the power keeps reducing. We went all the way from power 6, right? We jumped down step by step down to power 1 by far. See that now? Okay? And what happened with, I'm asking for the sixth derivative. Okay. That would be y, right? Sixth derivative of y, right? And then multiply that. Power 1 down, so it remains at 720, right? But now a constant. You guys following? Okay. I hate cutting my boards short, but I have to. So now we're moving into the seventh power, right? I mean, it's the seventh derivative right here. What do you say that derivative is? Zero. Okay. And what do you say the eighth derivative would be? It's all zero out, right? So for the rest of these guys, so starting at seventh derivative, right? And to the rest of those higher order derivatives, then those are all zero. See what I'm saying? And so that's also one nature of the power function that we can realize. Any power function, right? There's going to be a certain point, right? A certain order that it's going to start becoming all zero out on its derivative. Right? See what I mean? It squeezed out all of the powers and eventually it made it. It's going to make it a zero term like that. All right. Any other questions you guys have for me? Now I'll bring you some examples. One here, find y dx, the first derivative, right? And then d squared y dx squared, second derivative, right? And we also want to find third derivative. That should be good enough, right? So for any of the function I'm about to give in this example, that's fine. Those are three derivative order. So about our function here is y equals 2x cubed plus 4x plus 1. There you go. So with these problems with the primary scale, it should be quite simple. The zero derivative is the original function itself, right? First derivative, that's what it means. So go ahead and take that derivative. It's going to be what? 6 x squared, right? Plus 4. Look at that. We took the derivative out of that original function, so by top. Okay, so there's our y dx. And now advancing over to the d squared y dx squared, right? The second derivative. That's how we understand it. Okay. So that's making it to it. Constant term goes to 0. Now 6x squared here making it to 12 from x, right? We've got the second derivative, and the third derivative, quite straightforward. So from the previously found second derivative, right? So we gotta be able to find the previous one in order to move on to the next one right there. So there's no way to have a one step, from the starting function and to jump all the way to the third derivative. There's no way, right? You gotta be able to find the other guy before that. So 3y, right, over the x cubed here, d cubed y over the x cubed. Okay, you go. So from that, 12x, really now it's making it 12. You know what I'm saying? And so I'm not particularly interested in the fourth derivative or so on anymore, because for this thing right here, then starting with the fourth derivative, it's all going to zero out, right? Because these are polynomial. We've learned a little lessons from earlier lecture. Okay. All right. So with that, now still same example. Let me bring in part B of the example. How about sine y equals sine of x? Okay. That function, because along this example I want to draw out some other fascinating nature of the trig functions here. You guys will feel beneficial when you arrive at your calc 3. Okay, so ready for getting in? So the original function is here. So dy dx, right? dy dx is going to be, I need a reminder, cosine, agree? All right, yes, cosine of x. Sounds good? Okay, so now from that previously found first derivative, let's look for the second derivative. D squared y over the x squared, right? The second derivative. Negative sine, right? That's derivative here, negative sine of the x. Are we good? Okay, and again, now from that previously, from that just now found, right? I'm going to move on to d cubed y over the x cubed, which is the third derivative. You guys good with me on that, okay? That answer is equals, but don't forget now we have a negative coefficient. I mean the coefficient -1, right? So what's our derivative here? Negative cosine, right? Because there's a negative sign right here, so negative cosine of x. Right? Because the sign itself just comes out cosine, but then that negative sign counts in, right? So we got the third derivative and all that. Do you start seeing the looping nature right there? The going around nature, it's going sine original function, right? Cosine is swing over to the cosine, and then it starts swinging back to the sine, but with the opposite side. And then so that way it carried on to the next one being a cosine. Now our example only required us to finish here, but allow me for this one here, let me just bring it on scratch work here. So sort of like scratch work here. See? So sine of x, original function. Okay. So we found y prime, right, being cosine, as we already knew, right? And then we found y double prime being negative sine. Okay, that's the result we've had, we already found. And then y triple prime, right, third derivative, okay, minus cosine of x. So now what do you think is going to be when it's fourth derivative? And remember, when it comes to the fourth order or higher, I'm going to have to start using the superscript, right? The superscript with the parentheses is around right here. So what do you say this one is? It's going to be back today, sine of x, right? So now here's the idea. Think about what's happening beyond that. It's going to repeat that cycle right there. See what I'm saying? No? So fifth order derivative, right? The fifth derivative is back to a cosine landing exactly into this guy right there, right? That's what I meant by it's repeating the cycle again. And then there's a sixth derivative, right? Okay? It comes out being negative sine. It's repeating the cycle. That's landing exactly on this guy right there. And then the seventh derivative, right? It's going to be a negative cosine, right? And it's repeating this guy. And when it comes to the eighth derivative, another multiple of 4, right? Another multiple of 4 power, another order, right? Being the multiple of 4, it lands right back on the beginning one. See what I mean? Right? The cosine is going to behave the same, right? It's going to have a cycle right there, and every multiple of 4 order right there, right? Every multiple of the fourth order right there, and it's going to come back to the original function. Okay, so that's for the trig function. So let me go back to the other board. See, y equals 5 to the x. We've learned about how to calculate the derivative of e to the x, right? Prior to getting into this, right? So, first derivative, y prime, right? Or the dy dx, however you want to write it, right? What do I say about this? What would you say? Coefficient stays the same, right? All it matters is find the derivative of e to the x. What is the derivative of e to the x? E to the x. Agree? So it looks like the function repeats itself exactly, right? So now guess what? Y prime, the coefficient stays the same. Taking the derivative of this, what's the answer there? Another e to the x, right? And you take the third derivative, right? Meaning we take the derivative right on top of this. Coefficient stays the same, right? Taking the derivative of the exponential function here, the special e to the x, it comes out e to the x. All right, so that's something to remember about the e to the x. Now, especially if we've learned, higher order derivative, no matter how many times you take the derivative of that, right? That e to the x function stays the same. See what I'm saying? No? Okay. We still want to. We still want to do the similar work with that, but I'm going to bring it into a slightly more challenging work. That's why now I'm going to call it example 2. We still want to find dy dx, right? And also d squared y dx squared, right? And also the d cubed y dx cubed. The one I'm about to bring in now requires more attention. So how about y equals the square root of 1 minus x squared, for example. Okay, so let's find the first derivative, and then the second derivative, and then the third derivative. So, I mean, right at first look, it seems crazy, but as a reminder, before we even start into any derivative work here, think about rewriting this as 1 minus x squared onto the 1/2 power. You're good with me on that? Okay. And then, of course, these things right here, yes, the formal symbol for that, right? First derivative, dy dx. I could also go with y prime, that's right, making things a little simpler. General, right? There's some expression inside of a high power being the 1/2 power, right? Which I shouldn't even say high, but the point is some expression being inside of an overall power. So power rule says we multiply the 1/2 down, we keep the exact general structure with the inside there, 1 minus x squared, but we subtract the power here by 1, right? Making it to negative 1/2. You guys good with me on that again? And we multiply that with what? The derivative of the inside from the inside, right? So leaving it minus 2x. Does everybody agree with me on that? Okay? So now we are about to take the derivative on this. Right? Take the derivative on this. To get the d squared y, but see, this is why throughout all those times taking the derivative, I've been going loose about simplification, right? And you guys can see that on some of your exam questions, I even indicated you don't need to simplify, but think about it. Being able to simplify is a good ability because it's getting your work easier for the next step. See what I'm saying, huh? Right? So think about you can cancel the 2 here with that 2, right? Yep, and then that's making it right, minus x, right, times in product with 1 minus x squared to the negative 1/2 power. And then there are multiple routes that we can start with this one right here, but right here in the way how it looks now, right? I'm going to attempt with the product rule. You guys following what I'm doing there? Okay, because there's a product between the minus x and the whatever that is here to the negative 1/2 power. So product rule says, but that's the beginning of the second derivative. So taking the derivative of this product here, product rule says we take the derivative of the minus x, right? And sometimes when things get complicated, I'll just lay down the indication of the steps first, right? The planning of the steps first, and then we'll really do it later, afterward. And so that the derivative of minus x, and I'm going to multiply with 1 minus x squared to the negative 1/2, okay, no prime. And I'm going to subtract, now I'm going to leave the minus x the same, right? And I'm going to take the derivative of the 1 minus x squared to the negative 1/2, right? I'm going to take the prime of that. That's what I'm adding, right? It's product rule. Okay, so that's the product rule. And so now I'm going to really take the derivative. So the derivative of minus x gives me just negative 1, right? We good with that still? And then that one here, the factor we don't take the derivative, so let's leave it the same, 1 minus x squared to the negative 1/2. Okay. The next one here, well now it's ridiculous that we write it plus a minus x, so let's just write it as a minus x, right? But in product with. So now I'm going to take the derivative of this. So that derivative there, the negative power multiplies down, giving it negative 1/2, multiply down, right? I keep it in parentheses, and then I have a 1 minus x squared to the negative 3/2. You guys with me there? Right, because negative 1/2, subtract 1 away, try to take 1 away, making it negative 3/2. And then I'll multiply with the derivative from the inside, giving it minus 2x. See, that's inside part right here. According to the table, it gives me that 2x, minus 2x. Okay, and now we're gonna go ahead and once again cancel out some of these values here. So minus 2 cancel with a negative 1/2 like that, right? Making it positive 1, right? And then here is gonna be a negative term, so I'm looking at minus, right? 1 minus x squared to the negative 1/2, okay? And then minus x squared here, because the x multiplied with the other x, making it x squared, right? And then we were looking at 1 minus x squared to the negative 3/2. You guys following? Let's take some further reduction right here. You see, with this one right here, it's definitely good that we can reduce it. We can simplify it. So, how about for now? I haven't done this before, but for this starting at this point, things starting to involve multiple terms and things like that, right? How about let's rewrite it as a negative 1 over a positive square root of 1 minus x squared. There, I have to put back the root nature for a reason. And then here, as we're subtracting, now we've got x squared, right? But divided by what I have here is 1 minus x squared, right? To the 3/2 power. But I want you guys to recognize one thing. Isn't a 3/2 power on that means it's a square root of 1 minus x squared multiplied with, this one right here, this 1 minus x squared to the 3/2 power. On scratch word, it really means 1 minus x squared and multiply with the square root of 1 minus x squared. In another minute or so, you retrieve your algebra and we get back to that. More people agree with that? All right. So I mentioned of that for a reason. So how about this thing here? It's better to write it as this 1 minus x squared to the 3/2. So maybe on your paper you have more space there. So in the next step, write it like that. It means in the next step you got minus 1 over all that square root, right? Minus all of this here, but it's 1 minus x squared, right? Times the square root of 1 minus x squared. I wrote it like this so that we can easily see. It's making it easier to make a common denominator and start doing the combining it into one fraction. Are you following my plan right there? So now we got throughout our two denominators here, we already have the square root expression. So we only need to multiply the 1 minus x squared to the other side and negative 1 here, right? So that's making it now minus, and then I have 1 minus x squared, right? And then minus x squared, and then I'm putting that all over. So now I have the common denominator here is going to be 1 minus x squared, right? Times the square root of 1 minus x squared. In the end, being able to simplify an algebraic expression is still so vital, right? It helps into a lot of your work. And once I'm done with that simplification, you're going to see how it's making it easy for the next step, for the next level of the problem. So I'm not completely done with simplification yet, right? That's just how I made common denominator. Right? So the first term has become minus, in parentheses, 1 minus x squared. And then we subtract the other numerator. You guys following that? For some work. You see when the calculus work is easy to understand. It's easy to follow, but then a lot of times, once again, it's the algebra that keep holding us back with that, right? And then slowing down the process. Okay, but that's the part that you constantly need to get yourself fluid. So for my next step here, see we can make that now minus 1 plus x squared minus x squared. Technically I can move faster than that, but I want you guys to be fluid with this. So I just simply distribute it in the negative sign in front of that parentheses group like that. You guys agree with that distribution like that? And so now the x squared term cancel, right? And now that's making it negative 1 over. Now this here, once again, we're gonna smartly rewrite it. See, whatever expression form, it's just a choice. Sometimes we put in a choice and making it better for the next step. I'm gonna again rewrite this as 1 minus x squared, but to the power of 3 halves. There was a time I brought it down as a square root to see two separate kinds of factors, right? Making it easier for common denominator and all that. But now when we're done with that, we put it back in that form of being the power. So now this means our second derivative here has become minus, right? 1 minus x squared to the negative 3 halves power. You guys following? Right? All of that work there just to bring it down to something easy. And so I have to make some good comments here for everyone. So think about the example, or think about it as a picture of the problem. If you were only asked to finish up to second derivative, then right here is about good. See what I mean? Okay, right here is where you can, conclude your answer, right? Or here maybe, right? You can conclude your answer. You don't need to go all the way there a lot of times. But then because the problem is asking us to move on all the way to the third derivative, that's why simplifying down is better. Okay? The more simplification you can put on your current step, the better it is. So now I'm ready for the third one. the cube y over dx cubed, right? So now we differentiate right out of this. Because you definitely don't want to differentiate out of those ugly things over there, right? Making life even worse, right? Or a lot worse. So now there's a negative sign. Power rule says it's going to multiply down that negative power, right? Down in front, so making it now positive 3/2. You guys following? Right? The multiply with the entire 1 minus x squared inside of the roots. But that root now is minus 3/2 minus 1. What's the overall power here? Minus 3/2 minus 1? Minus 5/2, right? Okay? So all of that here, see 1 minus x squared, right? And minus 5/2. Are we good? But now once again, there's a little inside of that power we've been doing, right? So we need to recognize the derivative of that. We need to recognize that as the inside. So now chain rule says we take the derivative of that, giving me a minus 2x again. Are we good with that there? Right, so now with this thing here, I can make that now, see the minus 2, cancel with that 2, and we can rearrange the x to be multiplied in front. So now that's making it minus 3x, right? Multiply with the whole 1 minus x squared, okay, to the minus 5/2 powers. We only asked to find out up to the third derivative. We're done with that, right? We're done with that third derivative. So our work right here up to this point, any one of these is the second derivative, right? So that's the second derivative. And then we advance down to the simplification to the first derivative. So it's still the same kind of problem compared to example 1, but these problems here I wanted to bring them in so that I have to reinforce some algebraic simplification so that a lot of times when you're moving on to the next derivative like that, right, it's making life a little easier. Otherwise, if you stay with the original derivative right there and take the next one, it's going to get messy. It's really going to get messy. All right? All right. So for this one right here in part B of our example, yes, y prime, and let me just write the short notation with that. Okay? The y prime right here is going to be, recognize the logarithm right here, it's a natural log, right? So whatever the argument inside of our log, when we take the logarithm, it's going to go with 1 over 1 plus x squared. But then, once again, I was saying that earlier, whatever we recognize being the inside of our logarithm, that means we do have some inside portion of that, right? Chain rule is going to kick in and say, hey, we need to also take the derivative of the inside, right? Making it what?
2x.
2x, right? Yes, 2x. So now, as far as the derivative, the first derivative, we're done. Right? But it's better that we rewrite it a little bit. So there's a 2x, we're putting that 2x over 1 plus x squared. We want that still. Okay? So how about let's leave that first derivative in that form right there. And then we advance over to the second derivative. So seeing this as a quotient between the 2x, right, and the 1 plus x squared right there. The 2x over 1 plus x squared. So second derivative is going to be the derivative of the 2x over 1 plus x squared. Okay. So I'm going to see that as a quotient, so I'm about to use the quotient rule, right? So So here that gives me, the quotient rule says, and let's write it down as an indication of the plan right here. So the plan says we're gonna go 2x, take the prime of that, right? And multiply with 1 plus x squared with no prime. But we need to once again use the quotient rule. So I'm subtracting, right? And there's a 2x, right? And then 1 plus x squared with the prime. And don't forget, for the quotient rule here, we need to divide by the square of your denominator. So in that here, the derivative of 2x gives me just 2, right? And we multiply that with 1 plus x squared right there. And we subtract it. So now minus 2x, there's no prime of that, so it stays the same, minus 2x. But what's the derivative of 1 plus x squared? It's another 2x, right? Gives me a 2x, right? And then we got a 1 plus x squared all squared. That's now making it. And once again, at this point, technically we have done finding the second derivative, but we definitely want to, boil it down a little bit, right? Simplify it down a little bit. So let's distribute out that 2 for each term here. So in my next step, I'm looking at 2 plus 2x squared, right? Minus, now these two multiply together, making it a minus 4x squared. You guys with me there? And we got a 1 plus x squared all squared in the denominator. Let's one further step, simplify that. We can combine like terms on these, right? Making it, now the numerator is a 2, right? Minus 2x squared, and the denominator is a 1 plus x squared all squared. Look good? So at least the second derivative in this way right here is making it easier for the next step where we're learning to find, where we're finding the third derivative, right? So there's my second derivative. Okay, that's second derivative. Now the third derivative, triple prime right here, we're going to have to take the derivative on the 2 minus 2x squared over 1 plus x squared all squared, right? But take the derivative of that, take the prime of that. So once again, the quotient rule says we take the derivative of the 2 minus 2x squared first, right? And I'm just writing it down, so sometimes, like I said, when things get complicated, it's okay. Go ahead and lay down the plan first, right? Whatever rule, but lay down the plan according to that rule. And then we're gonna really get things taken care of piece by piece. So 1 plus x squared multiplied with that, that's the denominator, and we need to subtract, right? We go 2x minus 2x squared, we multiply with the derivative of 1 plus x squared all squared. Okay, you got that still? But don't forget, we need this difference here, we need to divide by, according to the quotient rule, right? The square of the denominator. So it's going to be 1 plus x squared, but we square it again means we're making it a fourth power, right? Because it was a square already and we squared it again, right? Making it a fourth power. Right? So that's just an indication of the plan, just sort of like a planning step right here. So now with this plan, it's giving us a clear instruction of what to do for the next step. So that denominator, let's just keep it here, 1 plus x squared, okay? On to the fourth power. Now that derivative gives me what? Constant term go to 0, right? That term right here makes that a minus 4x. Is everybody with me still? Okay. We multiply with the 1 plus x squared all squared, right? And then we're subtracting. Then the 2 minus 2x squared now stays the same. 2 minus 2x squared stays the same. And then now we're taking the derivative on that square right here. So there's a 1 plus x squared inside of the power, right? So be ready for chain rule. So here we're looking at, now we're looking at 2, right? Multiply with the whole 1 plus x squared, reduced down to the first power, right? But that inside right here, we have to take the derivative, making it a 2x. Right? All right, life's not so bad. Up to this point, I mean, it may look all over, but you see these are all in factor form, right? And then, so you can see that there's a common factor of 1 plus x squared, 1 plus x squared being the common factor. You guys need that? Okay, so let's factor it out. So there's a 1 plus x squared, right? 1 common factor. So now after factoring that out, we have the first term leaves behind with just the minus 4x, right? So that way, minus 4x, right? There's a 1 plus x squared left over, okay, from that first term. And now we're subtracting, there's a 2 minus 2x squared, right? Times 2 times 2x. Right? And now we're putting it all over that 1 plus x squared all to the 4th power. Right? And then the factor you can also go step by step. So now I think the point is no one is super good at anything. So even if I was doing it, right, I didn't recognize that this could have been another 4x right here, right? Being common factor with that. You guys follow what I'm trying to? So when we recognize another common factor, then we pull it out. So that's making a 4x, that's another 4x here with negative signs, right? We can factor out that negative sign right here, making it minus 4x. It's a common factor. You guys following? Right. And then 1 plus x squared, right? And then here, everything we have left in parentheses. Now just 1 plus x squared plus 2 minus 2x squared. Okay. Over 1 plus x squared all to the 4th power. Okay. It keeps getting reduced out, right? Simplify it down. Now I'm going to leave it for minus 4x here, the 1 plus x squared here, right? That here we can start taking away the parentheses, and so the 2 plus combined together with that 1 right here, making it a 3. The x combined like terms with that, right? Making it a minus x squared. We look at that. 1 plus 2, that's making 3x plus or minus 2x squared. I mean x squared minus 2x squared, making it a minus x squared. Right? And then putting that over as 1 plus x squared all to the 4th power. We look at that still. But now there's still a common factor in top and bottom here, right? We can also cancel that, making it only a power of 3 left over. So the final expression here comes out shockingly pretty simple. Minus 4x, right? 3 minus x squared all over 1 plus x squared all cubed. Right? And I can put that in final answer. Everyone's got to get your algebra back and go with it. Okay? This algebra stuff right here, I mean, the calculus stuff is easy to understand, but once again, the massive amount of algebra behind the scenes is what's getting a lot of us. Okay, so now let's look at another example here about our function here. F of x equals 4x to the 4th minus e to the x. And that's just part A. We want to find f prime of x, right, and f double prime of x. Okay, so another repeated practice for you guys. How about, let me fix that typo here a little bit. 5 e to the x, right? And we're asked to find f prime of x and f double prime of x. Okay, so this part is easy now. Taking the first derivative. Okay, that means we're going to take the prime on this. 4x to the 4th minus 5 e to the x, right? We take the derivative there. Term by term it gives me, so this term here gives me a 16x cubed, right? And that second term here gives me 5 e to the x. Look at that. So that's the first derivative. And now the second derivative here means we found the first derivative. And the second derivative, it's just a matter of taking that derivative on the first derivative. So 16x cubed minus 5 e to the x. Take the prime of that, right? And that's now giving me this. So 3 times 16 is a 48, right? X squared right there, and we're subtracting 5 e to the x again, because the derivative of that term stays the same. So now think about it. In a later problem here, same function, starting out, right? We first found the first derivative and second derivative. Okay, the reason we were doing that because there could be a time where you asked to find, hey, f double prime of 5, you see what I mean? There could be time that we're asked to find f double prime of 5, but the real problem out there could be, hey, here's your function. Here's your function. Find that. F double prime of 5. That means in our responsibility, we gotta go through these steps here first. We gotta find the f prime first, and then consequently, find the f double prime. And once you have arrived at the f double prime, then you now have a way to access that f double prime at 5, right? Right, so that's sort of like, I break it down into part A and part B, but it's one sequential problem right here, but ultimately we want to get f double prime of 5, yes, right? We want to evaluate f double prime of a value. So now That means equable prime of 5 is simply just, we take those results, right, and we substitute x equals 5 in there. And so you guys go ahead and have your calculator ready for some calculation for you. So we got 48, right, 5 squared, right, minus 5 times e to the 5th power. That's how we're substituting x equals 5 into the expression, right? And then 48 here is a 5 squared here is a 25. So we've got 48, right, times e products with 25, right, and then we subtract 5 by e to the 5th. We don't need, so I just need you to multiply this big number right here, right, and then here we can just leave that in exact expression like that. See what I mean? Right, so you guys go ahead and help me out with that, 48 times 25 again. Yeah?
I got 1,200.
1,200, okay, so you got 1,200 after 48 times 25. And then whatever that is, we subtract 5 times e to the 5th power. It's just the e itself is so irrational, so we let's decide to leave that in exact expression, right? So we're good with that. And then with your calculator power again, you can just type that in and precisely get the decimals, but there's no need for doing things like that. You know what I mean? Okay. All right. So there's your example 4 here. That's just one question out of that. Okay. There's no need to do too many questions. But this question right here, we're going to take you through some process with that, right? Because you were asked to find f double prime out of that given function. So that means what? It's strictly as a rule, in order to get second derivative, you got to have first derivative, right? Or if you're asked to, unfortunately, sometimes if you're asked to find a fourth derivative, you got to be able to find a third derivative. But in order to get third derivative, you got to be able to find second, right? And so on and so on. So these things have to go extremely sequential. Well, actually, we only asked to find a second derivative. So first derivative, you got to find it, right, in our responsibility. That's easy enough. Coefficient stays the same, right? The function here, the outer function is a logarithm, right? And the logarithm takes some sign of x inside. You see what I'm saying? That, right? So be ready for that. So now it's going to go what? 1 over sign of x, right? That's the rule for the logarithm being the outside function. You guys can read that? But then we must multiply with the derivative of the inside. I noted here, right? So the derivative of the inside is a cosine of x. That's good. So that means, and remember, it's best that we put it all in a simpler form. So 5 cosine of x over sine of x. Are we good with that there? There can even be a simpler way to put this. There can even be a simpler way of putting it. Remember, cosine over sine is a cotangent, right? So cosine over sine is cotangent. So I'm writing this here as 5 times cotangent of x. Sounds good there? So just the first derivative, I'd rather write it as a 5 times cotangent of x. So now we're ready for the second derivative. So meaning we take the derivative under 5 times cotangent of x, right? All of that skills you guys learned will come back. Right? So I'll leave the coefficient here the same, 5, right? And I'll take just simply or separately the derivative of cotangent. But now you guys can remind me again, what's the derivative for cotangent of x? Okay. One simple function. Yes?
Negative cosecant squared.
Negative cosecant squared, right? So 5 times that, right? The derivative of that, negative cosecant squared of x. I agree, right? So your final best answer, best looking answer, minus 5 cosecant squared of x. That's how we got it. See it, no? So it's all about, it's all about, hey, in order to find the next derivative, right, you gotta simplify it down, making it as the simplest as you can with that, right? So that, you know, the next work can be done more easily, right?